So we've got some terminology that we need to discuss, and then formulas that go with those things to decide the calculus that we're talking about. So page 249, I spread it out. He crammed it all together on his page, but you're certainly welcome to just copy paste. So when we talk about vectors, we're talking about component form, really. And so position vector is also known as the location of that particular object, whichever it is we're talking about, okay? So it's the component form of x and y, but it's going to be in parametric form at a specific time. Okay? So the position of the object, the location of the object at a given time. So x of t, y of t. Okay, the velocity vector. The velocity vector is just the derivative of x of t and t, again, in component form. Okay. Now, the speed is a formula you're going to want to know, okay, and use. It's like this. So we've talked about this notation before, velocity. But in this case, we're talking about speed in particular. And so here we're going to take the derivative of x, square it, the square root of all this. So again, another version of the distance formula. But we're using it in terms of the velocity. Okay, so this kind of takes out the positives and negatives, okay? That square root, obviously, is always going to be positive. I think we kind of talked about distance traveled yesterday. I think you had some questions about that in your homework yesterday. But in terms of vectors, what that's going to look like is this. So it is the integral from a to b, from whatever the starting time is, ending time. And then that's where we're going to take the derivative of the speed. And that will tell us, basically, you think about the area under a curve, that's the idea. From A to B, the area under the speed curve tells us the distance. And then, of course, the acceleration vector is just the second. Now, at rest is an important piece here. So when the object isn't moving at all, when the velocity vector is 0, 0. So this. What's important is that both the derivative of x and the derivative of y equals 0. It's not just one, right? Because if, for example, if x is 0, but y is not 0, it could be moving vertically still. It could have some vertical velocity. If x has a value and y is 0, then it could have some horizontal velocity. So it's really important that when you're doing a problem to determine when is the object at rest, that you're finding out the time when both the x and the derivative of x and the derivative of y equals 0. And they both occur like that. That's an important piece there for at rest. All right. Questions about any of that? I think this is new, right? Yeah, you guys haven't really done anything like this before. Okay, good. So here's an example. Example 1. Obviously, it's very small on the screen, but I do encourage you to screenshot that from your book because we're going to go through this one together. Unless you want to try it on your own, which you guys like to. What do we think? You want to try it on your own and then come back and do it together? You're already trying it on your own. Okay. So let's go through these. So of course, what I did, and hopefully you did this too, because those are the easiest points to test for time 0, 1, and 2, and you're just plugging them in and finding the corresponding points. So at 0, you have position 0, 4. At 1, we are at 3, 2. And at 2, we are at 12, 0. So hopefully you had that. And since that is happening over time, those points are traveling in that direction from left to right. So like that. Okay. And it's a little curve. Velocity vector at time 1. So the first thing you've got to do for the velocity vector is actually take the derivative. Okay. And so there's the derivative of v of t. Okay. And then you just plug in 1 in. So the velocity vector is 6, negative 3. Now the speed is a little bit different than we wanted at time 1. Because again, we're talking about taking that vector and squaring it in underneath a radical. So that's 36 plus 9, so square root of 45. That's going to be the speed. If you wanted to convert it to a decimal, you could, but that was good enough. Distance traveled, okay? So that's where we're talking about integration. And so having the velocity vector is important. We're just evaluating this between 0 and 3. You could simplify this stuff if you wanted to, or you could enter it directly in the calculator like this. Just again, be really careful with your parentheses and make sure that it's all under the radical. Sometimes typing that in, especially when it's, one of the things I found now that we work on iPads all the time, and if you make one little mistake, you can sort of erase that little mistake, but on the calculator, you can't. You got to start all the way over again. So it might be helpful to multiply it out if you struggle sometimes with finding all the right parentheses and all that. Okay, 28.583 is what you should have gotten there. Okay. Particle at rest. So when both of these are equal to 0. So that's, you're solving this equal to 0. Obviously t equals 0 there. And you have a couple situations you could have there. Okay. So that one's going to give me 0. That one's going to give me 0 at times 0 and 2. But the trick is they both have to be 0. Right? So at time 2, x is not equal to 0. So the only time when it is at rest is when t equals 0, because again, they both have to be 0. So when both of them happen, then, and if there's never a time when both of them equal 0, then the thing is never at rest. Acceleration vector. Okay, so now we're taking the derivative of the derivative, and then evaluating at time 2. Okay, and so that's just 6, 6. And then the last one, the direction. Okay. Direction, remember when we talk about vectors, we're talking about an angle. Bless you. Okay. And so, wow, I guess I didn't need to do that one. So let's do that one. I don't even have it written down. Let's see what, I sure didn't. Okay. So, time t and when t equals 2. So yeah, it is asking for two things. One, squeeze this in there. So at time 1, right, we know that the position is 3, 2. And then at time 2, we know that the position is 12, 0. Okay, so the direction at time 1 so this is theta is going to be the inverse tangent of 2 over 3, right? And at time 2, we're trying to find, let's call that theta 1, we'll call this theta 2, is at 0. Okay, so then it's just a matter of figuring out what those are. Do we have a restriction? Do we have multiple? So this one is 0. And then this one I need a calculator for. 3, 0.588. Cool. I did manage to cram it all in there. So yeah, whenever we're talking about direction, we're talking about the angle. So that's when we need the x and y. And of course, we already have the x and y. We already did that in part A. And so it's just inverse tangent of those. Okay. Sorry that I left those off. I don't know why I did. All right, next one. Any questions about any of those before we move on to the next one? Yeah. So yes, this can't be pi because that would infer that x would be negative and x here is positive, so that's where we go with 0. All right. Next example. Okay. Oh, I did do it on the next page. Come on, man. There it is. I was wondering, I'm like, man, there's not a lot of room to write there. All right, well, that makes me feel better about my presentation, even though I did all that for nothing. Okay, here's the next example. And we're not doing all of 2. I think there are more than just A and B, because I think the rest of them are things we've already did. So there's some new pieces in here that we didn't talk about there that I want to go through. Yeah, because the rest of it is stuff we already did. All right, velocity vector at time pi over 4. So we've got a particle moving. So they give us acceleration, right? They give us velocity vector, and they give us at time 0, and they give us its position at time 0. They don't give us the general component for velocity vector or the position, right? They only give us the velocity at a specific time, and they only give us the position at a specific time. So what we're going to have to do here is we're going to find the general velocity vector and the general position vector from the acceleration vector. We're going to kind of work ourselves backwards. On the last problem, we were given the position, we worked our way forward, so to speak, to velocity and to acceleration. And so, again, I think this is a good review of the relationship between position, velocity, and acceleration, and integration and derivative and all those relationships, okay? And what's going to happen here is we're going to be integrating, and the reason that we have the specific velocities and positions is because there's going to be a c involved when we integrate. Okay, so we need to be able to find those c's. All right, so for starters, the velocity vector is just the integral of this. Now notice I've got a c on each one. So when I integrate -2 cosine t, right, the integral of cosine is sine. So -2 sine t plus c1, right, because I'm going to have another c over here. And then here when I integrate sine, it's negative cosine. Okay, and so that's why the negatives cancel out. So this is where I'm at with the general velocity vector, not at a specific time. Now, what I can do is use that specific velocity vector that they've given us to solve for these c's. Because then I can have the absolute general velocity vector for this problem, and then I can evaluate it at time pi over 4. Okay? So, here's what we know. because we're talking about at time 0, the minus 2 sine of 0 plus C1 and 3 cosine 0 of C2 is going to equal 0 and 3. So this whole thing equals 0, this whole thing equals 3. And then we can find our C's from there. Okay, so since sine of 0 is 0, this is 0 plus C1, and this all has to equal 0, so C1 equals 0. And then over here, all of this has to equal 3. Cosine of 0 is 1. So I have 3 plus C2. And since the velocity vector, the y component is 3, C2 has to be 0. So this one's sort of a lead balloon, so to speak. Doesn't really, our C's are both 0. So what I really have here is negative 2 sine t and 3 cosine t, and so now I'm just going to evaluate that at pi over 4. And of course, the sine and cosine of pi over 4 is the square root of 2 over 2. So I'm going to get negative square root of 2 here, because the 2 and the 2 on the bottom are going to cancel. And then here I'm just going to have a 3 on top. So that is my velocity vector at time pi over 4. Now, how are we going to evaluate, how are we going to come up with the position vector for part B? Take the integral of the velocity vector. Now we know that both of these are 0, so it's really, we're taking the integral of negative 2 sine t and cosine t. So now that we've gone through that first one, you guys try the second one on your own. Okay, so those C's are still in play when I integrate both of those. It's not that we're integrating the C1 and C2 again. It's we're integrating, and I didn't write I maybe should have written that up here, that V of t is actually, and we figured that out after. Just wait.
It's a scheduled pass.
I don't care. They'll live. Whoever that is. Okay. Then I'm going to plug 0 in for t in both of these and set this one equal to 2, set this one equal to square root of 2 over 2. Okay, and I actually changed them to 3 and 4 since we already used 1 and 2. All right. So 2 is going to equal, again, what I've plugged in here. That's what the color is. All right. So in this case, since cosine is 1, this is all 2, so C3 equals 0. And this, of course, is 0, so C4 equals that. And then to evaluate at time pi over 4, we're taking 2 cosine, so really this is 0. So 2 cosine pi over 4. And then since this was the square root of 2 over 2, I'm evaluating 3 sine pi over 4 plus the square root of 2. So this is 2 times the square root of 2. So this is just the square root of 2. This is 3 square root of 2 over 2 plus the square root of 2 over 2, which is 4 square root of 2 over 2, which is 2 square root of 2.
Thank you.
Okay, there you go. How many had that? Good questions about any of that?